Time for part 2 of our time integrated equations. This is where we do some sample problems. I'm going to try and go through this kind of quickly, so you might have to pause if you're trying to write this stuff down along the way. So the first one, here we know that we have a certain reaction that follows this rate law that's given to us. When I look through this rate law, I see, I'll just rewrite this real quick. I see that my rate equals 0.00412. It's in molarity per second. I'm going to talk about units and how we can solve for these things later on. There is a little bit of a trick, but right now we're just going to go through the dimensional analysis and just use what we're given. And that is times the concentration of your original amount raised to the 0 power. The first thing that you need to get from this is that 0 is very significant. What that tells us is the overall order of that reaction. So that is a 0 order reaction. And based on that, we know that we can look back at our equations. You can either use the one that you're given, or maybe you even look at this problem and you say, okay, we're looking at our concentration falling from 4 molar to 2 molar. So you interpret that as being a half-life equation. So your equation for half-life for a 0 order reaction is going to be equal to your original concentration divided by 2K. You can just start plugging some things in. Your original concentration is 4 molar, and 2 times your rate constant is 0.00412, and the units again are in molarity per second. So when you go through this math, you end up seeing that your molarity cancels out, and you get your answer in 1 over 1 over seconds, which means it's going to be in seconds. I think you probably get 485, which really rounded to our 2 significant figures that were given in our problem, ends up being 490 seconds. Great way to do the problem. Let's say you don't like that because maybe you're second guessing your ability to memorize and understand or derive that half-life equation. There is no reason you can't just use the given equation, which for a 0 order reaction is going to be A minus A naught equals negative KT. So again, we plug in our information. I'm not going to write my units down in this example because it'll give us the same thing. It's going to be 2 minus 4 equals negative, our rate constant is 0.00412 times our t. When you solve for t, you again get that 490 seconds. So both of those are perfect ways to go through solving a problem like this. The important thing that you do up front is that you understand that this information is telling. It's letting you know that it's a 0 order reaction. All right, number 2. Here we have a certain reaction, has a rate constant of this, and it's known to be first order. That's important for us. And if the initial concentration is given to us, how long will it take for it to fall to a different concentration? So you should be able to look at those values and say, okay, well, it's not going to work to use a half-life equation because that's not half the amount. Again, you're told that it's first order, and because of that, you know to use this equation that it's the natural log of A over A naught is going to be equal to negative KT. So you can just start plugging some things in. Natural log of your amount after a given amount of time, your concentration after a given amount of time is 0.100 molar, and you divide that by your original amount, which is 0.935 molar. And that's going to be equal to negative of your K value, so negative 8.90 times 10 to the third, and that's going to be in years to the -1. You can write it however you want, years, 1 over years. We're going to take that and multiply that times T, which is what we're solving for. So when you go through solving, you get T equals 2.51 times 10 to the -4th, and that answer is in years. But the question is, how long is it in hours? So now the easy part, just a little bit of that dimensional analysis. 1 year is equal to 365 days. 1 day is 24 hours. So our final answer gives us 2.20 hours. Okay, so that was number 2. Now moving on to number 3. Don't let that fool you. It says tough, but it's not that bad. couple different ways to do this one. Here, again, it tells us the order of the reaction. It's second order, and it takes 50 seconds to fall from this concentration to this concentration. You can look at that and think to yourself, ooh, half-life, I could use that equation. Let's go ahead and start with that anyway. It does say how long will it take the same reaction to fall from this concentration to this concentration. Obviously, we're not going to be able to use a half-life reaction for that. What you should see that's missing is K. We need to be able to come up with a K value. That's why this first situation is given to us. Once we come up with that K value, we can plug that in for the second situation to be able to solve for our time. Okay, so first situation. I'm going to start by using my half-life reaction, which I know for a second order reaction is 1 over K times original concentration. So if I change this around, I'm going to end up getting, what will it be? It'll be K equals 1 over T1 half A naught. So when I plug this in, I get K equals 1 over, my time is 50 seconds, and my original concentration is 0.6 molar. So that's one way that we could do it, and we solve for K, and we end up getting that our K value equals 0.033. Well, what are my units in? 1 over seconds over molarity, so that sticks. We just keep it like that. If you don't like that way, again, there's no reason you can't use your original equation for the second order reaction that is given to you, which we know to be 1 over A minus 1 over A naught equals KT. And when you solve for this here, you end up saying 1 over the amount after a given amount of time is 0.3 minus 1 over 0.6, and that's going to be equal to K times 50. And again, you get that exact same value of K equals 0.033, 1 over molarity times seconds. So same thing. We know that we can solve for our K. Well, if you have your K value, now what you can do is you can plug that in to be able to use it with the second situation. So again, using this equation, we are going to say for our second situation that the amount after a given amount of time is 0.5 molar, that's our concentration, minus our original amount or concentration, which is 1 over 0.6 molar, and that's going to be equal to our rate constant, times time. Takes a second to maybe plug this in properly into your calculator. Eventually what you end up seeing is that you have molarity on the left-hand side, which is going to end up canceling with the molarity over here, and your time is going to end up being in seconds by the time it flips back up. So time equals 10.1, which really we should be rounding this, I guess, to 2 sig figs, so that becomes 10 seconds is our answer. Okay, wasn't that tough? We just had to do some 2 steps. Note that I did extra work in this. You don't really have to do this much work. I was showing you that there were 2 ways to go about calculating K. So we did twice the work on that part of it. Okay, number 4. Very tough. Well, not really. We don't even really have to do any math on this part, because when we read through here, we just have to think about the concept. You read through this problem, and it says a certain reaction starts out at 7 molar, and it takes 35 seconds to fall to 3.5 molar. So you should be looking at that and thinking to yourself, half-life. Then you read this next part. It says the same reaction takes 35 seconds. Wow, same time. That's what should jump out at you. Same amount of time to fall from this concentration to this. Again, you're thinking about half-life. So here is what's going on in your brain. You're thinking to yourself, there is the same amount of time regardless of the original concentration. same amount of time for this half-life, regardless of the original concentration. Look back at your half-life equations. You've got three of them, 0, first, and second order. Which one of those gives that situation? And there's only one of them. You should see that the first order is the only one. We can say first order is only equation that is independent of that original amount that you start with. Okay, so that wasn't that bad, but you have to think about it. You have to be able to relate it to half-life and look at what you've got in your given problem. Okay, number 5. This is when you need to make sure that you do have your diagnostics turned on in your calculator, and we are going to start plugging some things in. So I read through here and it says that we have this data. First thing we need to do is figure out the order of the reaction, because it doesn't give it to us. Then we're going to answer some questions based on that. In order to do this, we need to plug this information into our list. We know that we're going to have an L1 and an L2. What always goes into the L1, that's going to be your X, and L2 is always going to be the Y. In your L1, what is always the X in this case? And we saw this when we went through deriving these formulas. We saw that X is always going to be time. So here, this is my L1. And our L2 in this situation is going to be our concentration, which we're just going to say is A. But we need to figure out which order it is. So not only do we need to be able to compare time to A, just your concentration, you also need to be able to compare it to the natural log of A. And you need to be able to compare it to 1 over A. So what we need to do is we're going to be able to create a couple other columns in our list as well. We're going to come up with an L3 and an L4, and we're always going to compare those back to our time, is what we're going to do. Okay, so you guys know how to plug this in. Really, there's easy ways to do this. Instead of going through the calculations and then plugging those calculated values into your L3 and L4, there's a much easier way. So take a second, pause this, and get your L1 and your L2 plugged into your list. And then once you've done that, here's a calculator picture to show you what you're going to be doing. You are going to, and this is not a very good way for me to show this. I don't have a better way right now, though. So let's just do this. You've got your L1, you've got your L2, L3, and L4. So once you have everything in your L1 and L2, you are going to want to come over, highlight your L3 right up there at the top. You're going to bring that cursor up there so that it becomes dark. And you're going to see down at the bottom right here, it's going to say something about, it probably says L3 equals, and you're going to then, you want it to be equal to the natural log of your concentration, which is the natural log of L2. So you're going to hit, at that point you're going to hit second and list, which is that stat button, and that's going to give you a list of some different things. You're going to bring it down to L2. So in other words, so second list and then L2. In other words, by doing that, you're saying that you want your L3 to be equal to the natural log of your L2, and then you have to hit enter. You might have to hit it twice. Then all of a sudden, all of this data gets filled in. You're going to do the same thing over here with L4. You will go up to the top, and you will highlight your L4, and you're going to go to second. Actually, that's not true. You're going to highlight your L4, and it's going to come up and say natural log. It's going to come up and say L4. It wouldn't have been natural log. It would have been L3. Now we're going to see that it says L4 equals, and you're going to say 1 divided by, whereas earlier you would have said natural log, but now we're saying 1 divided by, and this is when you hit second function, then your list, and again you're going to scroll down and hit L2 and enter probably twice, I think. And then this will just all fill in. Hopefully that makes sense to you guys. Once you play around with it a little bit, I think you'll see that. So You have all that data now. You've got everything plugged into your L1, L2, L3, and L4. Now what you need to do is you need to be able to take those values and compare them to, you need to figure out the linear regression of a line. So let's see how I can write this. You are going to have a zero order, a first, and a second that you're going to be comparing because you've got all that data in your calculator now. So at this point, you will go ahead and you go up to your, let me erase these. You're going to go up here to your stat button, and now you would scroll over to calculate. You would hit linear regression, which is number 4. If you hit that twice, what that does is that defaults to doing the linear regression for L1, L2, which is perfect. That's what you want to do for that zero order reaction. And when you do so, you end up getting this. This is what you should end up getting for your equation for a line. Y equals negative 0.052x plus 1.527. And R squared value would be somewhere around 0.95. Doesn't matter if you look at your R's or your R squared, just be consistent between all of them. Okay, so you do that for your zero. You need to do the same thing where you're comparing, remember with zero, this was just comparing time to, what we're looking at here is time and concentration. For your first order, you want to look at time versus the natural log of A. So this is going to be comparing L1 to L3. So when you do this, again, you're going to hit your stat button and scroll to calculate, go down to linear regression, but don't hit it twice. Just hit it that one time and nothing's going to pop up after that. At that point, you tell it what to do. And that's when you say second, and then right down here is going to take it to that L1. So you're going to say second L1, comma, second, and then L2. And then you hit enter. Oh, not L2. Make that go away. We're doing L3. So that's what we want to do is L1 versus L3. So then you hit enter, and that's going to compare those two columns. And after you do that, you should get this. Y equals negative 0.074x plus 0.683. And in this case, our R squared value equals 1. Last one, do the same thing, and this time we're trying to compare T versus 1 over A. So in this case, we're going to be comparing L1 versus L4, which is, I think, right there, if I'm looking at that right. So L1 versus L4, and your equation becomes y equals 0.123 x minus 0.089, and r squared value equals 0.96. So now, why did we go through all of that? Because we wanted to come up with the one that most closely resembles a line. That's why you're looking at your correlation coefficient. That's why you had your diagnostics turned on. And this is the correct equation for that. It is first order. So we can come back here and we can answer that this is first order. I'm just going to rewrite this equation again really quickly because we'll need to refer to this. That y equals negative 0.074x plus 0.683. And to be able to answer the next couple questions, it says, what is the rate constant of the reaction? So in this case, our rate constant, we know that that's going to be K, and this is the information that gives us K. If you look back at your equation for this first order reaction, it's actually negative K. It's a negative slope. So It's got a negative here as well, so the negative and negative, it means that it's going to end up being a 0.074. It ends up being a positive value. At this moment, I am just going to give you the answer, and later on in this video, I'm going to tell you how you go about figuring these out. But the answer is going to be in 1/seconds. Okay, so we have just figured out our rate constant. Last little piece of this is the initial concentration. Well, we know that that's based on the y-intercept, but this is first order reaction. So our y-intercept, and maybe we can visualize this, that our y-intercept actually looks like this, where we've got natural log of our original amount. So that's what we're seeing. That's what our y-intercept is the natural log of our original amount, which we can read here as 0.683. Well, that's not what it asks for. It asks what is the initial concentration. So you guys can solve for this. You look back at your calculator, and it's really hard to see in this picture right here, but natural log right above it, it's that e to the x, so you have to use your second function key, and you end up finding out that your original concentration equals 1.98 molar. And that is it. You have figured out all of these guys now. Okay, we have one more problem, and then we're going to talk about units. Okay, this last problem, go ahead and take a second and plug all of that stuff into your calculator. Okay, so now that that is in your calculator, hopefully you've also plugged in your L3 and your L4, and you can go through and calculate the equation of a line. And we've got our zero, our first, and our second order equations that we come up with. You should have gotten y equals 0.123 x minus 0.089, and for first, y equals negative 0.003 x plus 0.83, and then y equals 0.008 plus 2.232. I did not write down my correlation coefficients for these guys, but I can tell you that r squared was really, really close to 1 on this one, on our second order reaction. That's what you'd be looking at. So that's the winner, and it was a lower number, lower values for 0 and first order. So to answer our questions, A, it is second order, and then B, remember question B asks for your rate constant. So if this is the winner right here, in a second order reaction, remember that this is a positive value. So we're looking at our K value is just that. It's going to be 0.008. And the answer is going to be as 1 over molarity times seconds. I'll show you why in a minute. And then the last little thing that we want to do is we want to figure out our concentration, our initial concentration. Think back to what that graph looks like. When you're looking at a second order reaction, you've got time here, and you've got 1 over concentration here. So in this case, you're really looking at 1 over your original concentration, which means that 1 over our original concentration equals this value, 2.232. Therefore, take the reciprocal of that, and your original concentration equals 0.448 molar. Yay, you have completed all of these. Last little tidbit here. The units for K. You can go through the dimensional analysis for this, but there's really a much easier way for us to think about it. And this is for K units, if you just want to write this down somewhere. That overall, what we're going to do is we're going to look at it as being 1. The units for K is always they're always going to be equal to 1 divided by your time times the concentration, which is always going to be molarity. And we're going to take that and raise that. This is still as part of the denominator. the overall reaction order minus 1. So for example, let's look at our 3 examples. We've got 0, first, and second order reactions. In every single case, we're always going to say it's equal to 1 divided by our time and divided by our concentration, which is molarity. Now what we have to do is we just have to raise those to the appropriate power. Okay, so I just rewrote that in every situation. In a 0 order, our overall order is 0, so we're going to say 0 minus 1 is raising this, and it's just this concentration that we're raising, to the negative 1. Well, what does that equal? You just take the reciprocal of that. So that's going to be molarity divided by time, which is quite often seconds, but it could be any unit of time. First order, we're going to say it's our overall reaction is first, so 1 minus 1 makes this 0. When you look at that, that equals 1, so that just cancels out, so your units are going to be in 1 over time. And then the second order, for your molarity, it's going to be 2 minus 1, so that's going to be raised to the first power, so it's just going to be equal to 1 divided by T times your concentration down there in the denominator as well. So that is it. You are done. Nice job.